In this video, we're going to talk about the indefinite integral, and this is chapter 43 from the notes. And so an indefinite integral is more or less an antiderivative, or more precisely a class of antiderivatives, or a class of functions whose derivative is the given function. Remember, antiderivatives are not unique. And so I'm going to look at three examples from this chapter. So 341, I'm going to look at part B. We have the integral x squared plus x to the negative 2 plus x to the negative 1/2. We find an antiderivative, which is just reversing the power rule all the way through. And then we add this c, this arbitrary constant. The reason we do that is, again, antiderivatives are not unique. C could be 0, and the derivative of this function would be this one. C could be negative 17, and the derivative of this function would still be this one. So remember, antiderivatives aren't unique, but they're unique up to a constant. So that means that we do have, well, a limited list of functions whose derivative is this. They all have this in common. The only way they can differ is by the constant. Part C is a little tricky. Part C will be easier to do when we get to the chapter on substitution, because this is a good candidate for substitution. But it's also something we can handle now simply by analyzing an antiderivative. So we have a function that looks like it was differentiated using the chain rule. So we have this fourth degree polynomial to a sixth power, and then we have this third degree polynomial right here. If we calculate the derivative of the fourth degree polynomial, we have 4x cubed plus 8. 4x cubed plus 8 is exactly 2 times this term. We'll keep that in mind. So let's find an antiderivative. If we were calculating a derivative using the chain rule, this would be the outside function. So we'll start by increasing the exponent by 1. We're going to reverse the power rule. So we increase the exponent by 1 and we multiply by 1/7. Let's ignore the rest of this for a moment. Let's just calculate the derivative of 1/7 times a fourth degree polynomial to the 7th power. 7 times 1/7 is 1. Decrease the exponent. That's what we have. Now the chain rule says multiply by the derivative of the inside function. So we would multiply by the derivative of this polynomial, which is 4x cubed plus 8. So that's what we have, but not what we want. We want 2x cubed plus 4. So how do we get that? We multiply 4x cubed plus 8 times 1/2. So that's why we have a 1/2 right here. And then plus our arbitrary constant. In the chapter on substitution, we will have an algorithm for doing this. We'll have a technique for calculating functions, antiderivatives of functions that were differentiated using the chain rule. So there is a more, I guess, algorithmic process to this. The last example we're going to look at is example 342. We're told two things about our function: the derivative and a function value, and we want to find the function. And as I've been indicating, well, several times in the last few videos, antiderivatives are not unique. That means simply knowing the derivative of f is not enough to tell us what f is. So we're given the derivative as 8x cubed minus 3. We know that f of x is 2x to the 4th minus 3x plus something, but we don't know what that something is. Antiderivatives are not unique, but they're unique up to a constant. We have to figure out what the constant is. Well, that's where we use the fact that f of 2 is 27. So f of 2 is 27. What is f of 2? F of 2 is 26 plus c, whatever c is. So f of 2 is 26 plus c, but we were told that's 27, so that means c is equal to 1. So our function is f of x is 2x cubed minus 3x plus 1.